Hello, this is Dr. Anna, your geology professor, and today we're going to talk about the second, uh, we're going to continue with the second segment of the groundwater chapter. Um, the last segment, I finished with the recharge and the discharge, and now we're going to talk about how the water moves in the ground. Uh, what makes the water move? Obviously, the most important force which plays a role here is the gravity, and so therefore because of the gravity most of the time the water is also moving from higher elevation to lower elevation. Sometimes actually when it's a closed system the water can move upwards, but that happens when there is a pressure difference. um, the pressure difference in the groundwater created by the height difference of the water table, and it happens sometimes. So it could happen that actually the groundwater is moving upwards. When you have a hill, the groundwater underneath there has higher pressure than if it would be in a valley. So the water from higher pressure areas will move to the lower pressure area. The scientist who actually worked out the rules of the water movement in the ground is Henry Darcy. He was the first so-called hydrogeologist, and this is what hydrogeologists do. They actually calculate the water movement and how much water in what area you got, and how much water you can take out without the pressure dropping so bad that it wouldn't actually come out. So Henry Darcy, he was a French engineer, and he did the calculations for water movements. And what he really realized, that if the porosity and the permeability is the same, and you have the hill and the permeability and the porosity is the same, then the slope will define how fast the water moves in the ground. The slope is basically the so-called hydraulic gradient, and that's what he did. He defined the velocity of the water against the hydraulic head. And there is this figure, and I mean, I could make it simpler, but basically what we got here is the slope, and this is the water table, and there is one well and the other one. So what we want to calculate is how fast the groundwater moves in this slope. And the way we calculated that, we're gonna get the elevation difference, which is the A, just like with the gradient. So that's the elevation difference of the water table from well to well. And the other one is the L, which is the distance between the two well. So, and the calculation is exactly the same. The hydraulic head, or the velocity of the groundwater, is going to be equal H over L. But because the water movement is underground, we have to take into account the type of rocks it's moving in. And the way we do that is that we multiply this with a constant, which is strictly or K. You can use K. Sorry, K. I said constant. So H times K, and K is basically a constant which is depend on the type of rocks here. So the speed of the groundwater in the rock is the elevation difference between the wells, divided by the distance between the wells and multiplied by the constant, which is related to the type of rocks. So this is kind of important, you should know it. That's the velocity of the water, or the hydraulic head. Now, the relationship between streams and groundwater levels. We have two kinds, the affluent and the influent. When the stream is affluent, that means that it's in a humid area. So you have a valley, it's a humid area, so the groundwater basically feeds the stream. This is the water table. And the water table feeds the stream. So the stream is supplied from the groundwater, and that just means that the groundwater is empty into the stream. Now, what happens when we do a dam, build a dam somewhere, and that just means that this valley is going to be filled up with water. I should use a different color. Filled up with water. Now, when you have this dam water and you got boats and stuff, motorboats, it's not a good idea because there is gasoline, and if, as you can see, right away, as soon as you have this lake, actually the lake water feeds the groundwater. So therefore, every pollution which is in the lake will actually go into the groundwater, and people surrounding the lake will drink that water. So if I were you at Smith Mountain Lake, I would not drink the groundwater because it could be very, very dangerous. Now, on the other hand, when the stream is influent, same situation. However, because the climate is arid in this case, the groundwater table is much lower, but below the stream it's higher than anywhere else. So basically the stream feeds the groundwater table. So that's the major difference. This is arid climate, and the other one is humid. This is kind of important to know. And I actually have a picture of it. So this is the effluent when the groundwater feeds the stream, and this is when it's arid climate and the stream feeds the groundwater. Now we are at the natural and artificial discharge. When we're talking about natural discharge, basically we're talking about springs. Anytime the water table or the perch water table intersects with the surface, you're gonna have a spring. And you probably all know about that there are superstitious people who think that springs happen for other reasons. But in real life, the thing is that anytime the water table reaches the surface, we're going to have a spring. Some of the springs, depending on where the supply of the spring is coming from, could have healing and treating power because if it comes from deep, where the temperature is higher, the water will contain more dissolved elements, which actually are just like taking pills, except the minerals are going through your skin, but the result is about the same. So sitting in waters which has high levels of magnesium and other very useful elements is just as good as taking pills. You might not know it, but actually the name of the science is balneology. Balneology, which is working with different springs and their healing powers. In Europe, it's very, very important. Actually, in this country, in California and Nevada, you've got a whole lot of hot springs, but people don't really know that they have healing powers. Okay, this shows a bunch of different kind of spring. Like in this case, there is limestone and shale. This is permeable and porous limestone, and this is shale. Here is the surface, and you got the spring right there. This one, we have sand, and this here is clay. So here we have springs. This one here, same thing. This is impermeable, and you got the springs right there. Same here. As long as you got a impermeable meeting a permeable and the surface, you're gonna get springs right there. On the other hand, if you don't have natural spring, then somehow you have to bring the water up. So this is what we call artificial discharge. Basically, this means that you drill or dig a well to bring the water up, and you're gonna pump the water. If the well is pumped, the groundwater in the surrounding area is going to be lowered, and we call that cone of depression. And as if you play the slideshow, this is actually an animated slide. In well B, they really pump it, so actually the cone of depression really goes down, and some of the neighborhooding wells are actually dry up. This is cone of depression. You will see it when the slide is going animated. Same here. So this is the place where we got to talk about the effect of pumping of groundwater, especially when there is no recharge. If there is no recharge in the area and people are using up, like in dry areas like the High Plains Aquifer, which is right here, the Ogallala, they have used up half of the groundwater, and it's a paleo groundwater, which means it doesn't get discharged. So as soon as they use it all up, there will not be water there. So they have really high pumping rate because they use it for agriculture, and there is about 50-meter water level drop already, which means half of the aquifer has been drained. So who knows what's going to happen when they use it up all. Now this is the Artesian system, and Artesian, the word Artesian comes from a French town where the first artesian well was drilled. It was an accident. They drilled into an aquifer, and actually they didn't have to pump the water. It was just coming out by itself. So what happens, the groundwater has to be confined, and because it's confined and it has to be tilted, and because of the confined like closed system, and the tilt is building a hydraulic head which pushes the water particles down, so it will build a pressure inside that closed system. And when you drill into that closed system, because of it's under pressure, the water will come up by itself. So to develop an Artesian system, there has to be 3 factors. Oh, before I go to the 3 factor, there is this slide here, and this actually is animated, and if you play the slideshow, it will show you how this projected water pressure surface, which is depending on the tilt of the aquifer, but the tilting, these are the aquicludes, and this is the aquifer here. Because of this tilt, there is a huge pressure difference, so depending on how much water is in the system, you have to have recharge. The projected pressure surface can go up and down. When it's completely filled, then this is the projected pressure surface, and you will see when it's animated. So in that case, both of the wells are positive, which means the water will come out by itself. But when it goes down like this, then both well becomes negative, which means you have to pump it. And this here, this slide just shows you the 3 what you need for it. And this is, so what we need an aquifer. It has to be pretty good aquifer. It needs to be confined, which makes it closed system by aquiclude, and it has to be tilted, have I told you, and it has to be humid climate because you got to have recharge all the time. So because of the tilt, there will be a projected water table, and if you drill into this aquifer, the water will always come up to the projected water pressure surface. So understandable, if the well is below that surface, you're going to have a positive well, and if it's above the surface, you're going to have a negative well. It's interesting that my brother have been living in Brunswick, Georgia for the last 30 years, and I never knew, but one of the most well-known Artesian system in the US is in Brunswick, Georgia. And this slide just shows you, of course, you don't have to know this, so don't even worry about it. I just put it in because it's interesting since my brother lives there. But as you can see, there is a lot of shale layer, the brown ones, and then the aquicludes in between. So these are like a multiple layer Artesian system. and it's really, really interesting. Now, if people want to have running water in their houses in big cities, you have to have artificial artesian system, which means the houses have to be under a so-called surface, projected water pressure surface for the houses to have running water. So in the cities, they actually build water towers. And the reason that they do that, they pump the water up into the water towers, and that actually will have a projected water pressure surface. And when the houses are below that surface, they will have running water. Okay, so that's just as simple as that is. And if actually you lose electricity because you pump up the water into the tower by electricity, then of course the tallest buildings are the first ones losing running water. So basically the city water system run by the water towers, and if you are in a hilly area, accordingly you need more than just one water tower, because this will not see the houses right here, obviously. So you have to have certain amount of water tower, unless the city is really flat and you don't have that many houses, then one water tower will do the supply. But if it's like hilly like Roanoke, I think Roanoke has like 6, 7, 8 water towers, because it's very, very hilly area. So now the next topic we're gonna have to talk about is hot springs and geysers. And hot springs and geysers will be common in recently active volcanic areas. And when a volcano erupts, like after that, like for thousands and thousands of years, the groundwater will be actually kind of hot, because the rocks stay hot from the volcanic eruption. So therefore, not drilling too deep, you can get high temperature waters, and that also means that this water will contain a lot of good elements for healing purposes. And the healing not only goes from through the skin, but people also drink this water, so they put the healing elements inside of their bodies. Um, Depending on how is it going, it could be hot spring or geysers, by the way. And most of the time the hot springs heat source is volcanic activity, but sometimes it could be that there is a fault line, and along the fault line the water comes up from deep, where the water is hot because of the geothermal gradient, if it's deep enough. So let's talk about the geysers first. In case of geysers, there is the magma chamber below. So this heat provides all the rocks being quite hot above the magma chamber. So the groundwater percolates into the fracture network, and becomes heated as it comes into contact with the hot rocks. When the water gets near its boiling point, a slight rise in the temperature or a little escape gas will instantly change it from water to steam. And because the steam expands suddenly, it will actually make the water come up to the surface very, very quickly. This is like an eruption of the geyser. After the eruption, the new relatively cold groundwater seeps into the hole again, and it has to be heated up, and then it will erupt again. So therefore, the geysers usually erupt very cyclically. Like Old Faithful erupts every 60 minutes, and so on. Like each geyser, they know how often, depending on how big the hole is. The bigger the hole, the less frequently the geysers, of course, because the water fills up the bigger hole, it takes longer for it to heat up. So therefore, depending on the size of the hole, the cyclicity of the geysers are changing. This just shows you one of the... Where do we have geysers in the world? We of course have in Yellowstone, Kamchatka, which is far east Russia, Iceland, of course, and in New Zealand. Those are the ones I know about, but there could be others. But I think these are the ones. Now, the other thing is when you have hot springs And I told you already that usually in the hot springs there is a lot of dissolved elements, and as the water comes to the surface, it cools down, and it won't be able to keep all those elements in solution. So there will be a lot of mineral precipitation around the hot springs or geysers. If you have calcium carbonate precipitation, we call it travertino or freshwater limestone. And if it is SiO2, which means quartz, then it's called geyserite. Like if you go to Yellowstone, most geysers will have geyserite around them, and the geyserite, the SiO2 makes the water amazingly blue, beautiful blue. And actually, if you go north, Mammoth Spring, then those are travertino deposits, because the geyser comes through limestone, so it dissolves a lot of calcium carbonate, and it makes travertino. And this takes us really to the geothermal energy. And if you have areas where the geothermal gradient is higher than normal, then relatively shallow wells can produce a lot of heat energy. And a lot of the places, they actually use the heat of the water for heating houses or making electricity. And this is what we call geothermal energy. And I know that there is an internet exercise which works with geothermal energy and how can you use it in your house. So I want you to really go through that and make sure that you understand. Most important countries where you have a lot of free geothermal energy is the West, California, Nevada, Oregon, Washington State, Iceland, New Zealand, and I know my country has a lot of it. We have a lot of hot springs, we have a lot of spa culture. See, when you have balneology, people using the healing waters, we call them actually spa. So going to the spa in Hungary means very different than going to the spa in the US, and I learned that in the hard way, because when I came to Roanoke, I saw all these day spas and I was thinking, oh my God, how cool. It's like being at home. There is all this cool place. But in Hungary, if there is a spa, that always means that there are all these really cool um, pools where people can just sit around and enjoy the healing power of the waters. And they always have swimming pools with this good water. So while you're swimming, your skin is just absorbing the really good elements.